Good day to everyone. My name is Harshiv, and today I'll be presenting my literature review report for CEG 5205. I'll be discussing two recent and complementary research papers, one focusing on artificial neural tactile sensing, and the other on a skin interface multimodal human machine interface for drone control. The presentation is divided into three major parts. First, I will review Chan et al. 2021, which introduces a bio-inspired tactile sensing system. I'll be looking at the introduction and background. I'll be looking at the methodology, the testing, the results, the conclusion, and future areas to explore. In the second paper, I'll be moving on to Yu et al. 2025, which talks about a multimodal skin interface for closed loop drone control. In this, I'll explore the introduction, the background, the methodology, the testing, the results, and the conclusion. Finally, I'll summarize the key findings and discuss how both of them work together to shape the future of human machine interfaces in different domains. So, moving on to the first paper, introducing it. The human body's non hairy or glabrous skin contains four major mechanosensory organs: Pacinian, Ruffini, Meissner, and Merkel corpuscles, responsible for detecting pressure and vibration. These are classified as slow adaptive and fast adaptive receptors. Most artificial tactile research replicates these receptors using piezoresistive, capacitive, piezoelectric, or triboelectric approaches. However, prior designs handled SA and FA separately, which often limits realism. So, in this paper, they propose the first dual mode sensor that combines both the slow adaptive and fast adaptive type sensors behaviors into a single thin film solution. So, this will help them artificially mimic a biological functioning of the skin sensor system. So, these diagrams also show the different type of sensors that are available based on previous works. Now, if we look at the methodology of this paper, the team fabricated a multi-layer T-skin using three key materials: RGO sheets for piezoresistive SA-type sensor pressure sensing, BATiO3 nanoparticles for piezoelectric FA-type vibration sensing, and a PDMS polymer matrix for flexibility and skin-like elasticity. These layers were isolated by a dielectric to prevent signal crosstalk between each layer. The device thus it achieves a simultaneous detection of steady pressure and transient vibration, which mirrors how human skin works, and it converts these into neural-like spike trains which are capable of direct nerve stimulation. This is shown in the testing phase. So as you can see in the diagram here, they demonstrate the small flexible skin, and they also show a visual diagram of how the layers are arranged in the artificial skin. Moving on to the testing phase, they basically conducted three tests: an ex vivo test using a mouse saphenous nerve, an in vivo test on a rat hind limb, and then they also did a finger simulation. In mice, the T-skin's SA and FA output signals were transmitted through afferent nerves that provide accurate neural-like signaling. In rats, stimulation of the hind limb motor nerve produced actual muscle contractions which showed functional biointegration. The team also built an artificial finger using this skin, and they trained a deep learning model to classify 20 different fabrics, which also achieved a very good 99.1% classification accuracy even on unseen textures. So these diagrams here, as you can see, they show some of the implementations. Like you can see over here, the hind limb of the rat. They've got the saphenous nerve, and they also have the finger simulation system here where they show how it looks like and how it's attached to the skin. And if you look at the results, The results clearly differentiate the SA and FA response profiles. The SA, the SA sensors produce sustained bursts, right? As you can see here, whereas the FA sensors spike only at touch and release. So if you look at the output torque here, they only spike at touch and release. So the torque output experiments confirm proportional responses to the pressure levels as well. Finally, the texture classification matrix, if you can see over here, uh, showed near perfect prediction accuracy, validating the system's ability to reproduce human like tactile perception. Finally, over to conclusion. To summarize the key findings of this work, Chun et al. Demonstrated dual mode tactile sensing that successfully mimics biological receptors. The system's neural compatible signals activated real nerves, its deep learning layer enabled artificial perception, and its flexible design offered strong potential for future neuroprosthetics. Future research may explore how the brain interprets such artificial signals using advanced neural recording techniques and how large scale neural signal databases could further enhance mimicking accuracy. This bridges the gap between electronic skin and biological nerves, representing a foundational step towards lifelike prosthetics. So, yeah, this is all about the first paper. Now, moving on to the second paper. So, in Yu et al., basically talks about drones, and they focus on creating a skin interface multimodal sensing system to improve the closed loop drone control. Drones are widely used these days in logistics, inspection, and transport, yet precise human control often remains a difficult task. Traditional joystick or smartphone interfaces are very unintuitive and slow and often have very limited feedback because you're still trying to control it using a phone or something like that. Previous attempts using EEG signals, EMG, speech, or vision based gesture recognition improve the control but lack tactile realism. This paper introduces a multimodal human machine interface that enables bidirectional communication between the operator and the drone. So, for example, you can probably see this is how traditional operators move their drones, and this is a diagram of how they implemented the system. So, looking at the methodology, the proposed system integrates three sensing modalities: gesture sensing using an IMU module on the hand to capture pitch, roll, and yaw. They use tactile feedback via a 3x3 matrix vibration actuator, or like a vibration actuator array, that is placed on the fingertips, providing the cues for orientation and airflow. Force feedback is the third modality, which is implemented through neuromuscular electrical stimulation, which is abbreviated as NMES, electrodes on the forearm, which give resistive sensations when the drone nears obstacles. All modules communicate in a closed feedback loop from user gestures to drone motion and back through tactile and NMES feedback, creating a natural, immersive control cycle. Looking at the testing study, so testing in this scenario basically focused on three aspects. They wanted to understand the tactile feedback accuracy. The 3x3 array achieved over 93% correct localization at 1.5x focus intensity. The IMU performance, the drone's pitch, roll, and yaw tracking remained highly stable even under headwind and crosswind tests. And the force feedback, NMES triggered reflexes, improved obstacle avoidance, and user reaction time compared with visual feedback alone. Going through the results, the IMU based control in this scenario achieved a real-time gesture tracking with correlation above 0.95 and latency under 50 milliseconds. And users accurately distinguished 9 tactile zones and responded instinctively to NMES cues, therefore reducing collisions by around 40%. The user study participants adapted faster and flew smoother flight paths with this control system um, on their hands instead of using conventional, like when compared to using conventional joystick systems, reporting higher realism and comfort. In essence, the combination of gestures, tactile and force feedback created a fully bidirectional interface that felt intuitive and lifelike. So, to conclude, Yu et al. Developed a thin, soft, and stretchable multimodal interface that unites gesture input, tactile vibration, force feedback, and FPV visual cues into one wearable platform. And the testing verified its stability in mechanical terms and precision in both sensing and feedback from and to the drone. The system, it therefore also enabled enhanced flight stability, rapid obstacle avoidance, and seamless user control, thus establishing a clear path towards immersive AR VR based robotics and assistive technologies. So, yeah, that's about it for this paper. And therefore, if we summarize the key findings from both papers into this small table, you can basically say that Chun et al. Focused on bio-inspired tactile sensing for artificial touch, using RGO and BATIO3 materials to replicate SA and FA neurons, whereas Yu et al. 2025 advanced this concept into a sort of different domain, into human-machine interaction, where they fused IMU, vibrotactile, and NMES feedback for drone control, while Chun's work enhanced biomimicry by attempting to implement an artificial skin system. Yu's system emphasized functional integration, attempting to bring a more natural approach by fusing sensation with a closed loop drone control system. Together, they demonstrate the evolution from sensing human touch to closing the loop between the human and machine interfaces. So, yeah, that's about it. And thank you for watching this literature review report. And both papers highlight, to conclude really, both papers highlight a rapid convergence of AI driven sensors, soft materials, and neural interface. Um, yeah, that's about it. Thank you.